Thank you, Jason. So I'll be talking about probabilistic inference in language models using twisted sequential Monte Carlo. This was work led by my student, Stephen Zhao, and postdoc Rob Breckelmans, and also jointly supervised by Alireza Makhzani, who was a research scientist at Vector at the time and has since gone on to work on alignment at Google. And Alireza came up with, I think, a lot of the key mathematical results in the work that I'll be talking about. Most of the slides in this presentation were made by Stephen and Rob. So why do we care about sequential Monte Carlo for language models? Well, this is very broadly motivated by the safety of LLMs. So even though this is work that we did at the University of Toronto rather than Anthropic, it's broadly motivated by the sorts of things that companies like Anthropic will have to deal with as the models get more powerful. Anthropic has a notion of AI safety levels that categorize the level of risk posed by an AI system. Currently, we're at ASL2, which is models that are believed not to be a catastrophic risk in themselves, but ASL3 could be triggered in the relatively near future, and this would be the first level of models that have catastrophic misuse potential. So being able to accelerate terror attacks and things like that. And so for models at that level, you want to be able to very confidently ensure robustness against jailbreaking. So you want to be able to do things like condition on the model agreeing to do something bad and figure out what was the prompt that led to that. For more powerful models, at ASL4, the models might have significant autonomous capabilities, like the ability to self-replicate and become independent of human oversight. And for models at that level, you want to be very confident that even once they won't attempt to carry out a complex, harmful plan. And so we'd be very interested in being able to bound probabilities of rare events, and maybe rare at the level of like 1 in a million or 1 in a billion, where you wouldn't be able to find it using simple Monte Carlo sampling. And so sequential Monte Carlo is a broad class of techniques from statistics. The particle filter is probably the most famous example. It's a very powerful set of tools for doing posterior inference in Bayesian models. But I think the thing that it's uniquely good at is estimating probabilities of rare events. There are a lot of techniques for doing inference, but SMC is one of the few that also comes with relatively accurate estimates of intractable normalizing constants. And so one of the main goals of this talk will be to relate standard LLM pipelines to sequential Monte Carlo and show that fairly small modifications of current procedures could actually be used to estimate probabilities of rare events through SMC. And so the point of this talk will be to essentially give a sense of what options we have, what's possible for us to do. This talk will also serve to unify fairly different approaches to steering LLMs. So in order to make SMC work in the context of LLMs, we need to learn what's called twist functions. These are functions that predict future evidence. They play a role roughly analogous to value functions in reinforcement learning. And so if you're trying to steer an LLM, there are two different kinds of approaches that are often used. You could try to do some sort of RL, where you reward behaviors that you like, punish the ones you don't like, or you might do some sort of test time inference like MCTS or beam search. And so twisted SMC gives a nice unifying framework for both kinds of strategies. And you can use both of them. You can choose design decisions and run algorithms to try to minimize a unified objective, which is the KL divergence between your approximate sampling distribution and the target posterior distribution. So it gives a unifying framework for doing things that are like RL and things that are like beam search. And we haven't looked at this so much in the context of language models in particular, but I'll show that in other contexts, sequential Monte Carlo often gives pretty nice scaling laws for the effectiveness of probabilistic inference. And if you saw the blog post from OpenAI when they released O1, one of the things they're most excited about was that they found consistent scaling laws for test time compute. How does the performance of the model on various tasks improve as you throw more test time compute at it? And so this is the sort of thing we might like to look for if we want to improve the use of test time compute in these models. So that's the general motivation. So I'll explain what is SMC. I'll motivate the general problem of controlled generation in language models. How do we sample from the prior modulated by something else we're interested in, like the reward from a preference model? And then I'll explain what is twisted sequential Monte Carlo. And then how do we learn twist functions that help us predict future evidence? And finally, I think the most distinctive thing that SMC is useful for, how can we use this all to estimate normalizing constants of distributions? Or how can we use this to estimate probabilities of rare events? I think there are certain situations in which we can get surprisingly strong bounds. Okay, so controlled generation in language models. I think a lot of you probably know much more about controlled generation than I do, but I'll use a fairly generic formulation where we have some model that we've trained. So I'll represent the prior distribution as P naught. This might be the autoregressive distribution defined by the pre-trained model. Or it might have also already undergone some RLHF training or things like that. It doesn't matter too much where you get the prior from. And and this model will generate a sequence that denote S1 through T. Each element of the sequence is a token from some vocabulary. And I'll use S naught to denote the prompt that it's conditioned on. And we don't have any reason to try to break down the structure of the prompt here, so I'll just denote it with the single variable S naught. And right, so maybe the user asks why they get a particular out-of-memory error, and the model returns a response. So we're interested in modulating the prior probability by some function that encodes some desired target behavior. And so for the purpose of this talk, we assume that this function phi is given, and this is something that's evaluated on the entire sequence. We don't assume we have any way to evaluate it on partial sequences. And so a canonical example of this would be a learned model of human preferences. So you could train a preference model using binary feedback provided by humans. You try to model the human feedback in terms of an underlying function R that encodes how much the user likes the response. And the preference is assumed to be a Boltzmann function of that underlying preference variable. So that variable R becomes the reward function for an RL algorithm. And so if we're trying to do controlled generation, we might have a potential, which is a Boltzmann function of R, e to the beta times R. Right, so sampling from that should bias the model's responses to things that humans would approve of. All right, so we have a target distribution, which is proportional to the product of the prior times the potential. And importantly, we can evaluate the unnormalized distribution, right? We can evaluate the prior times the potential, but it's not actually a probability distribution because it doesn't normalize to 1. So it's easy to evaluate the unnormalized distribution, and I'll generally denote unnormalized distributions with tildes. So we're trying to sample from P tilde. But unfortunately, we can't compute the actual probabilities because it depends on an intractable denominator. The denominator requires summing over all possible sequences. This gives the normalizing constant, often called the partition function, denoted with the letter Z. And so the intractability of this is much of what makes inference challenging. In general, I'm going to drop the explicit prompt from now on. So I'll just leave out S0 because we're not going to have any reason to try to pick that apart. That's just going to be shared between everything that we do in this talk. All right, so what makes the inference problem challenging is that the potential we're given is evaluated given a full sequence, right? You can evaluate a human preference model on the whole sequence, but if you try to give it a partial sequence, maybe it'll give it a low rating because it's incomplete or something like that. So it needs the whole sequence. And that's difficult because when we generate from LLMs, we like to generate autoregressively, one token at a time. And it's very difficult if we get the important information only at the end. And so we'd like to somehow learn to generate autoregressively from a model like this. So this might involve learning an approximate autoregressive policy Q, such that sampling from Q comes as close as possible to the target distribution. And in order to do that, we might also like some measure of the quality of partial sequences. So we'd like to learn functions psi t, which I'll explain in just a bit. And we'd like these to be good estimates of the evidence that we'll get in the future. And ideally, what we'd like to have sampled from in each step is the posterior marginal, right? So this is the target distribution or posterior distribution, but marginalized over everything that comes later in the sequence, right? So we have the target distribution that's defined over the whole sequence that we sum over all of the future time steps. And so if we're trying to learn such a queue, you might think about doing it using some sort of RL, but I'll be arguing that we can take a probabilistic perspective to this, and this gives us more options. We can use a wider variety of algorithms for adapting the proposal distribution and these functions psi, and we can also kind of surprisingly evaluate how well we're doing in certain cases at matching this distribution. All right, so now I'll just make a slight notational change. So we've been talking about the inference problem in terms of an arbitrary potential phi, but sometimes it's more convenient to think about this from a Bayesian perspective. So we imagine we have some observation that we get at the very end. Maybe we have a binary indicator variable that tells us whether the model said something harmful or whether it got the correct answer to a math problem. And so we'd like to condition on that variable. These two approaches are equivalent because the probability of the outcome, that's one thing you could use for the potential phi. And conversely, you could encode phi in terms of some sort of observation variable. So just a few examples of this. So one kind of controlled generation we might like to do is we might have a classifier that's defined over full sequences. So maybe we'd like to sample from book reviews conditioned on the sentiment being positive. That's something I'll use as a running example in explaining SMC. And so essentially the potential phi corresponds to the probability the classifier assigns to the model, to the sequence being in that category. Particularly, yep.
So some people in the audience will know that as the problem handled by the fudge paper, controlled generation.
Yep. Yeah, so fudge is a great example of how to learn a twist function. Yep. So I think a particularly interesting example is infilling. This is
star paper. And that's the star paper.
Yep. This would be a great way of doing star.
Yep.
So we're trying to condition on future tokens. So in the case of safety, maybe we want to condition on the model responding, here's how to make a bioweapon. We want to predict what did the user say that led to that response. It's difficult to do because this is not an autoregressive sampling problem. There might be some binary indicator function we're interested in, like did the model get a math problem correct? This is the sort of sampling that STAR is trying to do. And then there's also the example I gave earlier of RLHF, right? We have Boltzmann potential in terms of the learned reward function. And that's the one that it might be least obvious how to view as posterior inference. But you can basically translate this into conditioning on observation by defining a biased coin whose probability of coming up heads is proportional to e to the b times r. And then you just have to choose a normalizing constant m that's at least an upper bound on the possible values of the potential. So in principle, you could do this inference problem using rejection sampling, right? Just keep sampling until the coin comes up heads. But in practice, the probability of heads might be just unrealistically small for any particular example. All right, so one naive way of doing inference in these sorts of distributions is importance weighting. So you assume you have a proposal distribution. This might be the prior distribution, but there are I'll talk about ways that we could try to adapt it. But we have some proposal distribution, and we generate sequences from that proposal. So maybe we're trying to do sentiment analysis. We're trying to generate book reviews conditioned on positive sentiment. So we generate a bunch of sequences, and then we evaluate the sentiment. And so there's one that we liked. This book was bad, a disappointing experience. That's an unsuccessful sample. And so we generate these sequences, and then we score them according to importance weights. That's just the unnormalized target distribution divided by the proposal distribution. And then if we want to get a posterior sample at the end, we just sample one of these sequences proportional to the importance weights. And so we're much more likely to sample the green ones than the red ones. And so importance weighting is an algorithm that in principle it's consistent. You can keep throwing more samples at it and eventually get accurate estimates of the correct distribution, but it might take an unrealistically large number of samples in practice. There's a classic paper by Chatterjee and Diaconis that actually kind of analyzes the number of samples you need and finds that it's exponential in KLPQ, the mass covering KL divergence. So if you do a good job of covering the full distribution, then you might be able to do importance weighting with a reasonably small number of samples. But in general, it's going to be a very inefficient procedure. All right, so like before we get to actually SMC, even just adapting the proposal distribution, we can already relate to things that are done for LLMs. So we're trying to adapt the proposal distribution. We'd like it to be as close as possible to the target posterior, so that our importance weights wouldn't have too high variance. What distances could we try to minimize? Well, I think maybe the two most obvious ones would be the KL divergence in either direction. So we could try to minimize the mode seeking direction of KL divergence. That will try to find one mode. It'll try to fit the mode well, but it'll try to avoid producing anything that's very low probability. On the other hand, we could try to minimize the mass covering direction, try to cover all of the modes of the distribution. And there's an interesting connection, which is that if you're doing the sort of policy gradient that's normally done on LLMs, that's essentially a way of doing this mode seeking KL divergence. So there was an interesting paper by Tomek Korbak from a couple of years ago that argued that RL training of LLMs with a KL penalty, right? So you typically regularize it by penalizing the KL divergence to the initial policy. That's essentially viewed as Bayesian inference, right? The optimal solution to that is the Boltzmann modulated distribution that I highlighted earlier. And if you do gradient descent on this, that's essentially the policy gradient update. So so the gradient of the right, so minimizing the KL divergence is equivalent to maximizing the expected reward minus some multiple of the KL divergence to the prior. And if you compute the gradients of this, you get a reinforced like update. Right, so you take the log probability gradient of the thing that you sampled, and then you multiply it by a value that depends on the reward and the ratio of probabilities for the prior and target distribution, and optionally a baseline that helps reduce the variance. And so we're already learning proposal distributions, whether we like it or not. But we also have the option of adapting the distribution in the mask covering direction. So you could essentially, right, so the mask covering direction would be like doing maximum likelihood on samples from the distribution. We don't have exact samples, but we could try to generate approximate samples using importance sampling or a more sophisticated SMC algorithm. And this direction seems advantageous from the perspective of proposal distributions because we'd be more able to make use of test time compute, right? If you're going to generate a bunch of particles and then prune the bad ones, then maybe you're willing to put mass and bad stuff as long as you cover all of the good modes of the distribution. And so this is not exactly what was done in the STAR algorithm, but I think it's similar in spirit, right? So generating a bunch of samples and training on the correct ones. I think the way this differs from STAR would basically be that you also include the importance weights for the ratio of the prior over the proposal probability.
Can I inject one other?
Yep.
So what Roger is calling here, I guess, mode seeking and mass covering, or sometimes mode seeking and mean seeking, sometimes called exclusive and inclusive directions of KL divergence, if you've seen those terms.
Mm-hmm. All right, so so what about sequential Monte Carlo and what about twist functions? So the idea is rather than generating full sequences and filtering them only at the end, maybe we can notice ahead of time if we're generating things that aren't going to work, right? So if you have a partial sequence that starts, this book was bad, it's probably not going to be positive sentiment, and so we should be able to eliminate that right away. And so particle filtering is a classic algorithm that's an instance of sequential Monte Carlo and would let us essentially prune things early on. So what we do is for a partial sequence, we compute an importance weight, right? But importance weight for what? What's the distribution that we'd like the particles to target at any particular instance? Well, I claim that the distribution we'd like to target is the marginal target distribution, right? So the target distribution with everything in the future marginalized out. And so if we had an oracle, what we'd like to compute is this ratio of p tilde, the marginal p tilde, divided by proposal distribution q. We can't actually get this, but if we had this, what could we do? Well, right, so we marginalize over future tokens. And so we do a resampling step where we sample particles proportional to their importance weights. So we lose the bad particle, keep the good ones. And then we continue generation from those partial sequences. Then we evaluate those and so on. All right, so we don't have such an oracle. What can we do instead? Well, we'd like to learn intermediate target posteriors. So these involve future likelihoods. And this is known in the SMC literature as twist functions. And so we'd like to learn a function such that the target distribution, the marginal target distribution, equals the prior distribution times this function, which is denoted PT star of the observations given the partial sequence. And the thing we'd like to compute is essentially the target distribution marginalized over all of the remaining time steps. And so it's possible to show that these are the optimal twist functions. And so what we'd like to do is we'd like to learn some functions psi that come as close as possible to this optimal posterior. And so we're going to have intermediate distributions denoted as pi tilde. These are unnormalized distributions because it might be useful to keep track of estimates of the normalizing constant. And these will be defined as the prior distribution times our learned twists. And so we'd like some criterion that will give us twists that are as close as possible to the integral of future evidence. Yep.
Okay, this might be a rather tough question, but I'm wondering if when you do this, does it increase the like difference of like label bias and stuff like that, especially as you're using these unnormalized intermediate target distributions?
What do you mean by label bias?
I think that's trying to fix label bias.
You think we fix it? Okay.
I think that's the goal, but it's like, yeah.
Sorry, what do you mean by?
Label bias is something like, for instance, like an sequence token or something where all kinds of probability mass gets assigned to something. So when you have like the full sequence and you're doing a scoring full sequence, right? If you do something like normalize it, it will not penalize longer sequences or something like that. Label bias basically once you get to something where you get to a choice and everything after it, there's a very limited choice or very fixed amount of probability. You just keep going with that, and often as like sequences get longer, it gets more prevalent. I don't know if that's it.
Yeah, interesting.
So that, I mean, since you haven't heard the term before, label bias is a term introduced by Andrew McCallum and colleagues for explaining why they were using CRFs rather than maximum entropy markup models, and they identified the problem. They should, instead of calling it label bias, they should have called it failure to look ahead. So this is trying to learn a look ahead function, which is analogous to the cost to go function in A star, except A star is maximizing and this is sampling.
Right. So then, but I mean, if you're doing the sampling, it should prevent it. I think we get something on it. Yeah.
Yeah, I think based on this discussion, this is something that twist learning is meant to address, but I would have to think about it more carefully. All right, so in order to sample from the sequence, given the learned twists, we would propose from the proposal distribution. And then in each step, we compute incremental importance weights. So the formula for the importance weights over the whole sequence can be broken down as a product of terms associated with each of the individual samples. And so we update the importance weights in that way in each step. And sometimes we resample. And when we resample, we reset the importance weights of each term in order to avoid double counting the evidence. Then we continue sampling from each of these sequences, and we resample and so on. Okay. And so SMC is a fairly broad class of algorithms. It includes particle filters. There are also other things you can do, like you can take MCMC steps that preserve the intermediate distributions and things like that. And there's a very interesting property that SMC algorithms share, which is that at the end of the algorithm, you get an unbiased estimate of the normalizing constant of the distribution. You can sort of show that each of the steps preserves that property. This is not as useful as it sounds. So I'll explain later in the talk what it actually means to have an unbiased estimate, why that might not be directly useful. but it will still be a useful property for deriving other things from the algorithm. All right, and so that's why it's useful to have twist functions. Yep.
I think I didn't follow how to say.
Yeah. So the formula for the weights, like I'm not sure if it makes sense to like, dig into the details of this formula now, but it essentially comes from, if you just write out the importance weight for the full sequence, that's going to be the ratio of p tilde over q for the whole sequence. And p tilde and q can both be written down as products of terms associated with each of the individual tokens. And so this formula here is just those incremental terms associated with each token, right? The reason for breaking it down like this is just so that whenever we do the resampling step, we can reset the weights of the particles so that we can avoid double counting evidence, right? If we didn't reset them, then the particles that already looked good would get resampled again, and eventually they would be they would make up too much of the distribution.
Oh, this is site.
Right. The size are the twist functions. These are supposed to be the approximations of future evidence. And so I guess the intuition is that, if you look at the term on the right, the ratio of the size, this is saying that if psi t is larger than psi t minus 1, that means that we now think this particle is better than it looked a time step ago. And so we should increase our importance weights. Okay, so this is why it's useful to have twist functions. And how can we actually learn them? And I think it's interesting that we have quite a lot of options available. And we can roughly divide these into things that are closely related to RL algorithms and things that are not, things that are more fundamentally probabilistic. And so it's interesting how we have fairly different literatures that have all been working on essentially the same problem. So there's the SMC literature, including twisted SMC algorithms that learn twist functions. There's the area of entropy regularized RL. So you wind up with a lot of algorithms that are similar to standard RL algorithms, but involve soft maxes rather than maxes and things like that. And so there's an algorithm, soft Q learning, which is essentially like learning twist functions if the prior is a uniform distribution. So Jason already mentioned the fudge algorithm. So that's one way of learning twist functions. You're essentially directly fitting a regression to predict future outcomes. Right. So if you could do that perfectly, then that would be, I think, an optimal twist function. And so when we published this paper, we also introduced an algorithm that we called contrastive twist learning. I learned just yesterday that Jason had a paper in 2018 that I think is very similar to this. I'd have to read it in detail to understand the relationships, but this is something that we'd come up with. It seemed fairly natural, and it was pretty hard to find a reference in literature that did exactly this. But I think that paper was fairly close. But anyway, what this is we'd like to adapt the twist functions in order to make what we sometimes call the filtering distribution look more like the smoothing distribution. So the filtering distribution is the distribution over partial sequences given the evidence that we have only up to that time step, right? And in the case of of our problem, we don't actually get any evidence until the end. But we can think about the sequence with the learned twist functions as being sort of like a filtering distribution. We'd like that to look more like the smoothing distribution, which is the posterior given the information from the full sequence, right? The marginal target distribution. And just like with learning the proposal distributions, if we'd like to make use of test time compute, if we'd like to be able to generate lots of particles and prune the bad ones, it would probably be useful to have a mass covering objective. So how can we adapt the twist functions in order to cover as much mass as possible, right? How can we minimize KLPQ? I'm sorry, so the sigma here should be a P tilde. So we'd like to minimize the KL divergence of our intermediate distributions to P tilde. And when you derive the maximum likelihood update for that objective, you essentially get the difference of two expectations. So one of them is the expectation of the log likelihood, the gradient of the log twist under the smoothing distribution, right? So the importance weights at the very end of the algorithm. And then we subtract from that the expectation of that same log twist gradient, the expectation under the filtering distribution. So the importance weights using the intermediate twists. And so this is essentially the maximum likelihood update rule for an energy-based model. And so it's trying to cover, it's trying to minimize the mass covering KL divergence. So this is our contrastive twist learning algorithm. I think we include this largely as an example of something that this probabilistic framework buys you beyond just the analogies with RL, right? And so I think if we're trying to build an SMC sampler incrementally, maybe whatever value function you get from an RL algorithm would be a reasonably useful twist function to start out with. Twists are like value functions, but then maybe you can do better if you target an objective that's explicitly trying to match the target distribution. All right, so that's all I'll say about learning the twist functions. But I think the most maybe unique and interesting thing we get from all this is the ability to estimate normalizing constants. And so how does that work? So if we think about minimizing the mode-seeking KL divergence, we often see that in the context of like variational inference, like in variational autoencoders, we have the elbow objective. So the log normalizing constant can be written as the elbow, the evidence lower bound, plus the gap between that and the true value, and that gap is the mode-seeking KL divergence. And so if we're trying to optimize the proposal distribution, and now we're back in simple importance sampling land, where we can forget about SMC for the moment, the simple importance sampling, right? If we're trying to adapt Q to minimize the KL divergence, this is also equivalent to maximizing the elbow. Right, so somehow posterior sampling is equivalent to estimating lower bounds on normalizing constants. The optimal choice of Q would be just P, and that would make the KL 0 and would make the bound tight. And so the sampling version of this algorithm, we sample from the Q distribution. If we want to know how well we're doing, well, we have a lower bound on the true value. And so the higher the lower bound, the better we're doing. We don't actually know the KL divergence because we don't know log Z. So we can tell maybe if one algorithm is better than another, but we don't know how close they actually are to the true value. So So that's how we can estimate the log normalizing constant with a single sample, but we can also do multiple samples and do simple importance sampling. And so, as I said before, if you're trying to approximate the normalizing constant for an intractable distribution p tilde, we can compute importance weights, which are the ratio p tilde over q. And those importance weights are an unbiased estimator of z, right? The expectation of those weights is z. And so that might sound like a useful property, but it's not actually that useful on its own, because the thing that makes it unbiased is that, well, you might completely underestimate the true value 99.999% of the time, and occasionally sample something very, very large. And so these weights could have large variance, potentially even infinite variance. So this unbiasedness property is not a free lunch. You can combine multiple importance samples, right? If one sample is unbiased, then you can combine k of them and it's still unbiased. But this estimator might have lower variance. And this is sometimes known as the I-way estimate in machine learning because it was used in the I-way algorithm, although the actual technique long predates the I-way.
You might want to spell out I-way.
Oh, the importance weighted autoencoder. All right, and I think a more useful way to view this unbiased estimate of z is as a biased estimate of the log normalizing constant. And this basically follows from Jensen's inequality. So we have this estimator whose expectation is z. We can instead take the log of that estimator, and that will underestimate log z in expectation. So that's just Jensen's inequality. And I think this is a more useful way of thinking about it, because at least this estimate will tend to have pretty reasonable variance. Right? It's a biased estimate, but reasonable variance. All right, so we can still evaluate these methods by saying, well, whichever one returns a larger value is probably better because they're all lower bounds. And if we want to return like a single approximate sample using this method, we just do that with, we just sample proportionally to the importance weights. So that's the sampling version of the algorithm. Okay. And so this improves with larger k. You can actually show that the bound gets strictly better in expectation as you increase k. And at least in principle, it's consistent, although probably not in practice. All right. So all right. So that is the elbow story. That's how we get lower bounds on log z. But that's not always the direction we want, right? If we're trying to rule out malign behaviors of an AI system, we probably want to upper bound that probability rather than lower bounding it. And it's kind of interesting that there's also a corresponding upper bound that mirrors the elbow. So we call this the U-bow, or evidence upper bound. And you get this just by flipping the roles of P and Q in this equation. So just flip the roles and shuffle some terms around. And so essentially you have this upper bound, which says you compute the importance weights, but the particles are sampled from P rather than from Q.
They're sampled approximately from P in practice because you're going to use SMC approach.
Well, so this is the catch,
Yeah.
right? So this bound exists in theory, but we can't actually compute it in practice, right? So but in theory, we have this upper bound, and the gap between that and the true log z equals the KL divergence in the other direction. Okay, but this is impractical because this requires being able to sample from P. And so it seems like we're stuck, right? Is this just maybe a theoretical curiosity? And let's see. All right, and I'll first mention another interpretation of these bounds. So I talked about the importance sampling bound. It's also possible to demonstrate something, demonstrate the same thing for SMC in general, right? This all follows from the unbiasedness property. But there's an interesting interpretation of it, which is that you can define an extended state space that keeps track of all of the random decisions over the course of the algorithm. So if you're running a particle filter, you keep track of all of the individual chains. Whenever you resample, you keep track of the ancestry variables. And so you have this extended state space, and you can view the elbow estimate as just simple importance sampling over that extended state space. And this sounds like it probably makes things worse, right? Because if you make the space larger, then surely the KL divergence gets larger. But it actually turns out to work because once you add all these extra variables, you can define the target distribution in a way that actually gets much closer to the proposal distribution. And so it all actually works out. And so this construction, I won't go through in detail here, but it gives a recipe for how to construct the upper bounds for SMC. And this is one of the, I think, the more interesting contributions that Ali Reza came up with. Basically, an extended state-based recipe for thinking about SMC resampling. And so we get both lower and upper bounds in principle. And so, right, so we talk about elbows all the time. Why don't you ever hear about U-bows? Well, of course, the reason, as I said, is that it's very hard. And the intuition for why it's hard is that if I want to demonstrate a lower bound on the normalizing constant, like I just have to demonstrate a mode of the distribution, right? I can say, well, I found this probability mass, so I have a lower bound. The upper bound requires demonstrating that there isn't some other mode that you've missed. Right, so it's like the difference between demonstrating like a satisfying assignment versus proving unsat. But surprisingly, there's actually one situation in which it's practical to get an upper bound. And it turns out that what you need is a single exact posterior sample, right? A single exact sample from P. And that sounds hard. How do we get an exact sample? And so this is the idea behind a method that I proposed back in 2015 called bidirectional Monte Carlo. The situation where we can get an exact sample is if the observations are sampled from the prior, right? Because then we just have to keep track of the latent variables that we use to produce that sample. And those latent variables turn out to be an exact posterior sample. And so in the context of language models, the main case where this helps us is infilling, right? Conditioning on future tokens. Now, unfortunately, we can't do this for infilling from arbitrary future tokens. We can only do it from tokens that the model generated. But this would still give us a way of maybe evaluating the accuracy of our inference procedures. And so just to give a flavor of how this works, this is from my 2015 paper introducing the method. We were interested in evaluating marginal likelihood estimators for Bayesian models. And so this was, I think this is a Bayesian clustering model, I think a finite version of the Chinese restaurant process. And we tried out 4 different algorithms for estimating the marginal likelihood. And they all seem to level off as you feed them more compute, but they're leveling off to different things, right? So like, should we trust any of them? Fortunately, some of these are lower bounds. So AIS and particle filtering give lower bounds. So we know that the true value is somewhere in that range, but it could still be much larger than all the others. But when we do the BDMC trick, and this is for synthetic data generated from the prior, running AIS in reverse is an instance of the upper bound, and that actually basically matches the forward AIS bound. And so we can actually identify the true marginal likelihood with very high confidence and high precision. I didn't actually say this, but we know something a little bit more than that. The lower bound is a lower bound in expectation, right? That's all we get from Jensen's inequality. We can actually show pretty strong tail bounds, that the stochastic lower bound is very unlikely to overestimate by very much. And so we can actually be pretty confident that we have the correct value here. And so given that, we can actually evaluate lots of marginal likelihood estimation algorithms and compare how their error scales with the amount of computation fed in. And we see that there are two algorithms that we considered here that will actually give you good answers if you give them enough computation. That is yield importance sampling and particle filters. And so scaling laws, right? We like scaling laws, and this is a way to get them for inference algorithms. All right, and so, yep.
Right, before you move on, it might be worth reminding the students, especially why it would be useful to estimate the like model selection or.
Oh yeah. So like, why are we interested in marginal likelihood for Bayesian models? That's the classic model selection criterion in a Bayesian context, right? So it's the probability of the observed data with all of the model parameters and latent variables integrated out, and so it rewards models for being able to fit the data well, but it also incorporates a very strong Occam's razor effect, because it gets penalized for there being a small volume of posterior probability mass assigned to the correct answer, right? If it requires a lot of bits to locate the correct parameters in this space, then it gets very heavily penalized in the marginal likelihood. So that's why we'd be interested in computing this. All right, and it actually turns out we get a little bit more than just bounds on the normalizing constant. We can also, in the case of synthetic data, we can also bound the KL divergence from the true posterior distribution. Right, so I said that the gaps between the estimate and the true value, the gaps in expectation, are the KL divergences of the approximate samples. The KL divergences between the approximate samples and the true posterior in this extended state space. Okay, and the KL in the extended state space is an upper bound on the KL between the final samples at the end of the algorithm, and that's a consequence of the data processing inequality. Right? When you marginalize stuff out, the KL goes down. And so we can use this to give an upper bound on the KL divergence of our approximate distribution of approximate samples from the target distribution. And so just to summarize things, we have the true value log z, which we don't actually have the ability to compute. We can always get the stochastic lower bound. We don't need exact samples for that. And in the case that we have an exact sample, right, if we're using synthetic data, we can also get the corresponding upper bound. And so the gap between the lower and upper bounds is the Jeffreys divergence, which is the sum of the KL divergences in the two directions. And so that's the KL divergence over the extended state space. And that's an upper bound on the KL divergences over the final samples. And so a follow-up paper from 2016 used this method to derive bounds on KL divergence for some probabilistic programming problems. This one was a matrix factorization. The top two curves are using a very generic, I think it might have been some sort of like Metropolis Hastings search in the web people probabilistic programming framework. The bottom curves are doing Hamiltonian Monte Carlo in Stan, and we see pretty good scaling from HMC. So one of the things we demonstrated in the paper that's the main subject of this talk is that this all works for transformer language models. We were working with very small models in this work, mostly just because of the infrastructure we had, not because of inherent limitations of the algorithms. The algorithms use essentially the same operations that are used in the large models, and so the actual cost should be fairly comparable to whatever inference algorithms are typically used. But we were working with small models here, and so this was an example where we took the tiny stories. Model trained in tiny stories. And so it's something that's very unlikely to produce text that would be classified as toxic. And so we're doing an inference problem conditioning on the text being classified as highly toxic, right? Probability more than 99%. And you have to generate a lot of Monte Carlo samples in order to get that. It requires like 100,000 samples before you get something classified as highly toxic. And so can we estimate the normalizing constant for this algorithm? And so if we first consider using the base model as the proposal distribution, right, this is just the naive prior. If we just sample from the prior, then we completely fail to estimate log z. So that's the two orange curves. If we do intermediate resampling using the learned twists, then we can actually get pretty close to the true value.
Can we interpret this as figuring out the probability that the base model would generate something toxic?
That's right.
Yep. Which might be useful to know, and it's small.
Mm-hmm. Yep. And then there's kind of a neat other thing we can do. I mean, so far we've been using the twist functions just for resampling. We could also try to fold them into the proposal distribution. And so we can fold the twist functions into the next token prediction, essentially just add the values to the logits whenever we resample. That gives us a better proposal distribution. And that actually turns out to work very well in this context. So this is the green and blue curves. So the blue curve is without doing the SMC resampling. And that just, with very little computation, gets us very close to the correct value. I mean, it requires doing the twist learning, but once that's done, it's very efficient to do the sampling. And in this case, it turned out there wasn't really a further benefit to doing the SMC resampling. I think folding the twist functions into the proposal seemed to work just fine. So I think the interesting thing about this result is just that we're able to do this estimate, get things to converge to the correct log z, and bound the probabilities and the KL for practical language models. Okay. And we can compare the various approaches for learning twists. The contrastive twist learning procedure that we propose is pretty competitive against other things that have been proposed in the literature. It doesn't always win out, but often wins out, and seems to do especially well in terms of the inclusive KL divergence which it's trained for. So I think this is a useful thing if you're trying to do posterior sampling. All right, and so basically twisted SMC gives a unifying framework for things that are like RL and things that are like beam search. And so essentially the prior distribution is like the initial policy if you're doing RL. The proposal distribution behaves like the policy. Twist functions are like value functions, and resampling is like beam search. And so if you have a pipeline for doing controlled generation in an LLM, it might be that you can fairly simply transform it into an SMC algorithm and be able to get these probability bounds and things like that. So, right, so we can get the probabilities, and we can also use the probabilistic framework to target mass covering objectives, which might be more useful in the context of test time inference. So I think I'll leave it at that. Thank you.
So I'll ask one, based on your slide where you mentioned PBO.
Mhm.
When there's two methods and they both do well, of course, one always thinks about hybridizing. And
Mm-hmm.
so, could you imagine using the twist model as an initializer for PPO, or maybe better yet, if you're running DPO, you need a
Mhm.
reference distribution that you're trying to stay close to.
Yeah, I mean, I think we might just, want to combine these different objectives, right? I think targeting like KLPQ plus KLQP
Yep.
is a pretty sensible thing to do. And arguably it might be even better than either one individually because right. I mean, maybe it's like maybe a mode seeking algorithm might learn to cover only a subset of the distribution, like a common phenomenon in training LLMs to be harmless is that they just learn to completely avoid certain topics, right? Mode covering algorithms can, like that solution. You might train them to be mask covering, but they put a lot of probability on bad stuff. Forcing it to do both simultaneously, it seems like it might, actually force it to learn to model the details of the riskier parts of the distribution. So I think it definitely seems like an interesting thing to explore.